Hi everyone, I am with another important and conceptual book McConkey from the chapter number 5. So two reversible heat engines operate in series between source at 527 centigrade and a sink at 17 centigrade if the engine have equal efficiency. So both the engines that is provided in this problem have equal efficiency, working on equal efficiency. And the first reject, so the heat rejected by the first one is 400 kilojoule to the second. So both the engines are operating in series. I will draw the schematic diagram first. So what we need to find the temperature at which heat is supplied to the second engine. So then heat taken from the source and the work done by the engines. Assume that engine operates on the Carnot side. So before solving this problem 5.2, I will make a sketch, a schematic diagram that will help you in understanding this problem. Okay, so this is the high temperature reservoir. So you can say that this is the heat source. So heat source, we call it is at a temperature T1, that is at 527 centigrade. Okay. So below it there is a heat sink. So here is heat sink. That temperature is T2, that is 17 centigrade. Okay. So this heat source transfer heat to the engine that give you output in the form of work, that is W1, because this is the first engine E1, I'm noting it from E1. So this engine deliver and reject heat at Q reject. So it is the rejected heat by the engine 1, that is 400 kilojoule. Okay. So then another engine that come in its series that deliver you the output work is W2, and we say that it is engine 2. And then finally the heat is delivered to the heat sink, and in this way the two engines work between higher temperatures and the lower temperature reservoir. So in between this, that the heat that is rejected from the engine 1, we call it is at a temperature Ts. So this is the temperature to which heat is supplied to the second engine. So this S represents the second engine source, you can say. Okay. So these are the sketch and the concept behind this problem 5.2. If you understand it carefully, then almost 60% story is covered. Now the rest is just calculations. Now come to the solutions now. So these are the foundations that I delivered you. Now come to the solutions point of view. T1, that is 527 centigrade, just add 273 to convert that into Kelvin, it will be 100 Kelvin. Now and T2 is 17 centigrade, just add 273 to convert it into Kelvin, so it will be 290 Kelvin. Now here the condition is given have equal efficiency, so both the engine, here is the engine, so this is engine 1, this is engine 2, so both the engine work on same efficiency. So engine 1 efficiency will be equal to engine 2 efficiency. Okay, now so we will write the efficiency of engine 1 and engine 2 in terms of its corresponding temperatures difference, higher temperature and lower temperature. So that will be equal to 1 minus so the temperatures of the engine 1 is heat supplied at T1 and rejected at Ts. So the Ts is rejected and T1 is the heat that is supplied, is equal to 1 minus heat supplied, heat rejected is T2 and heat supplied is Ts. So this one will be cancelled with this one and 1 minus become plus. So this Ts divided by T1, that is 800, and this T2 divided by Ts, and this T2 is basically equal to 290. Okay, so multiply this 800 and 290 and this Ts become square, so it becomes Ts square, and this is 290 multiplied by 800, take under square root. So this Ts is the temperature that is rejected by the first engine. So just by using the calculator you will got it value is that is 481.6. 481.6. If you convert that into centigrade, just subtract 273 from it, you will convert that into centigrade. And it will be 208 centigrade roundable. Okay. Now the next step is to, so this is the first part of the problem 5.2. The next part is of the problem 5.2 is work done by the heat taken from the source. So the heat to which heat taken from the, so we have to find the heat source. This heat source we have to find. So Qs is interesting to find. Before finding this heat source of the from which heat is taken continuously and delivered to the engine 1, we must be familiar with its efficiency. So we will find the efficiency with the help of the temperatures of engine 2. So 1 minus what are its temperature variation, that is T2 divided by Ts. So this engine 2 works between these two temperatures, T2 and Ts. So the supplied temperature is Ts and deliver or heat sink temperature is T2. So that's why supplied temperature is right below here. So 1 minus T2, T2 value is 290 divided by Ts is 481.6. So the efficiency of the second engine will become 290 divided by 481.6. So you will got the efficiency is 39.7 almost. But the efficiency of the engine 2 is the same as the engine 1 because as it is already given in the statement. So now we have to find this Qs, heat delivered by the heat source. So now the efficiency Q of this is equal to efficiency of the first engine, that is, so we also know that efficiency is equal to heat supplied minus heat rejected divided by heat supplied. Now the efficiency 1 is equal to efficiency of the first engine. I am talking about first engine because heat is supplied from the first engine from the source Qs. So this QS will be cancelled out with this, so it will become 1. So this is Q rejected divided by Q supplied. And now the efficiency is 1 minus QR rejected is given, that is 400 divided by Q supplied. We have to calculate, and its efficiency is 39.7%. So 0.3 in terms of, we have to write its numerical value of the efficiency. So after simplifications you will get these equations, then using the calculator you will find the value, what type of answer you will expect. So 400 divided by 1 minus answer and then bracket enter. So the heat supplied for the first engine is 664 kilojoule. That is the heat supplied, and is the second part of this problem 5.2 problem. Now the third problem, the third part of this problem is work done by each engine. So now we are moving toward the final part of this problem. So work done by first engine, that is equal to Q heat supplied minus heat rejected. So heat supplied is 664 that we have calculated right now, and heat rejected is given, that is 400. So if you subtract this you will find the heat output of the work done by the first engine. So use the calculator, minus 400. So it is 264.2 kilojoule. Okay. Now for the second engine work output, heat is supplied minus heat rejected. So for the second engine, heat supplied is 400 and heat rejected is unknown. So we have to calculate first the heat rejected by the second engine. So we know the formula, efficiency formula of the second engine, that is known, and that is 0.397. In terms of heat, I previously write down its derived equations. So it is the heat rejected divided by heat supplied. So efficiency is 0.397. 1 minus, so Q rejected for the second engine we have to calculate, and Q supplied, heat supplied for the second, this S subscript is in the second engine, is already given, that is 400. So putting the value, now the things are getting very easy now. 0.397, 1 minus Q rejected, we have to calculate, and heat supplied is 400. So we are near to end the problems. So Q rejected from the second engine is 400 into 1 minus 0.397. Now use the calculator to find its value. That is 400 into 1 minus 0.397. So that is 241.2. So its value is 241.2 kilojoule. The work output we obtained by the second engine is Q supplied, that is 400, minus Q rejected, that is 241.2. So the work output from the second engine you will get is very simple now. 400 minus this answer, that is 158.8. 158.8, so around about 159 kilojoule. I hope you understand this problem 5.2. More problems from the book McConkey is on the way. Please subscribe my channels and share with your friend, so most and more people and students can get benefits from these lectures and videos. Thank you so much.